what the crystal field ground states are and the type of exchange interactions that come about with these lattices. One thing to point out is that the anisotropy in the lattice is actually a local anisotropy. So the Z direction is pointing into or out of the tetrahedra. So the well-known spin ices, they have moments that point only into or out of the tetrahedra, but there are other power chlorines which have XY-like G tensors like this, which is sort of perpendicular to that direction. So how we have come to describe these materials most effectively is through this 4-parameter pseudo-spin 1/2 Hamiltonian. And the 4 parameters are exchange parameters, and we often write them down like this: JZZ, J plus minus, J plus minus plus minus, and JZ plus minus. And what these parameters do is couple different components of these sort of pseudo-spin 1/2 operators. And so this is the full Hamiltonian here. And as experimentalists, one of our things that we can actually do quite effectively here is determine what these 4 parameters are, and then try to understand what the ground state of the model would be compared to the material. So for a terbium titanate, what we know now is that there is a very XY-like G tensor. So the moments like to be in these planes that are perpendicular to the ice-like directions or the Z direction. But what we learned is that there's actually a strong exchange coupling between the Ising components of these moments, or of the pseudospins. And in addition to that, there's a strong coupling between the planar and Ising components, the JZ plus minus. So let's look at one of the problems here. So a terbium titanate has an anomaly in the low temperature specific heat around, let's say for now, 200 millikelvin. But the problem is that this is not a constant temperature for each sample. And furthermore, there's a different sort of sharpness associated with these peaks in different samples. But fortunately, most of the powder samples have the very high temperature, 265 millikelvin, and very tall, sharp anomalies, indicating that they have a higher quality and less variability from powder to powder. The single crystals, on the other hand, have sort of this sort of feature where you have a lower temperature anomaly from, say, 170 millikelvin up to 220 millikelvin. And in fact, all of the single crystals have a pretty low peak height associated with this anomaly. And so, correspondingly, there are some variations in the magnetic ground state that we know about. So, for instance, some of the samples show evidence for a ferromagnetic transition at this anomaly, and others, like some single crystal samples, do not show any evidence for a long-range ordered state. Okay, so for those samples that do order, the size of the ordered moment is coded from around 0.8 to 1.14 magnetons, which is about 47 to 64% of the total saturation moment of the ground state doublet. Furthermore, some samples show evidence for hysteresis at the transition, which confirms the first order nature of these transitions. So let me show you some results that we've had since 2009 on a single crystal that has this type of specific heat. So it's actually got both signatures in it. It has the signature from the higher temperature transition and the lower temperature anomaly. But I'll point out here that the peak height is rather low. So one of the things that's quite interesting, and you'll see actually persists even in the best quality samples, is that as you cool down from, say, 4 Kelvin to 30 millikelvin, the energy versus momentum, SFU and omega, that you get from inelastic neutron scattering doesn't really change all that much. So you have this kind of broad continuum-like scattering, which is, this would be in the paramagnetic state, doesn't seem to really be modified by this transition very much at all, and certainly you don't see any sharp spin wave excitations that you would expect from an ordered ferromagnet. In addition, in this single crystal, what we see is a large amount of diffuse scattering. Here I'm isolating it. It's actually quasi-elastic in nature, so I'm isolating from 0.1 to 0.3 millielectron volts just to show it better. But what happens as you go through the transition here is you don't lose this diffuse scattering, and instead you start to see it build up closer to the 111 Bragg peak, almost as if it was trying to become a long-range ordered state, but doesn't quite make it there. Yeah, so in this single crystal, we do not see any signs for a long-range ordered ferromagnetic state. But one thing that we could do, and this ended up being extremely useful, is that we can apply a magnetic field to the single crystal samples and then measure the inelastic excitations as a function of field. And as you see here, if you apply a small field of 0.25 Tesla, you start to lift up this diffuse scattering, and it starts to organize itself into these sharp spin wave excitations. So this is a signature that we're entering a field polarized state. And if you go to high enough fields, you can imagine that this could be well described by a linear spin wave theory, which is what we did. So working with Leon Valence and Lucille Fabry, we were able to fit our data to this anisotropic exchange model. And you can see here we did this for 2 field strengths. And let me point out that the
気象庁、先ほど栃木県県央部に大雨警報、栃木県南西部に大雨洪水警報を発表しました。土砂災害や河川の増水に警戒してください。繰り返します。気象庁は先ほど栃木県県央部に大雨警報、栃木県南西部に大雨洪水警報を発表しました。土砂災害や河川の増水に警戒してください。
はい、というわけで警報ですね、くれぐれもご注意いただきたいと思います。さて、栗原さん、すいません、中断して、途中で、はい、この法案の中身で、まだまだ未回収の、まだ未召集の遺骨があるということですよね。
はい、100万柱以上のですね、遺骨、ご遺骨を、今年度から10年間かけて、集中的に、国家の責任として収容しようというのがこの法案の眼目です。
はい、戦後70年というこの時期というのはどういうふうに考えればいいでしょうか。